As I mentioned in the previous foil, domino, if you want to use domino as a series of stages, so one domino stage followed by another domino stage, the actual domino stage itself needs a inverting stage in between, which means that a series of domino stages needs to be non-inverting. Domino stage is inverting, followed by the static stage in between to the next domino stage. So you always need non-inverting from one stage to the next. So how do we, if we want to perform an inverting function, one of the ways we can do that is using what's called dual rail domino. And what this does is, instead of just performing a single function with a single domino gate, what we can do is we can take the pull down logic that we have in our NMOS for the domino pull down logic, and we can create a set of inputs and a logic function that's complementary to it, that has, if the inputs, so if we have inputs supplied that are A and A bar, B and B bar, then we can create one pull down stack that uses the A, B, and C inputs, for example, and another pull down stack that uses A bar, B bar, and C bar inputs, and we modify the pull down stacks so that they're complementary to each other. And that way, when one is discharging, the other one is guaranteed to not discharge, and vice versa. So they're always the inverse of each other. We have true and complementary or inverted versions of all the inputs, and we get true and inverted outputs from the domino stage. So as you can see below on the lower right, I'm showing a dual rail domino circuit structure where you have two pre-charged devices clocked by the same clock, and you only need one foot device clocked by that same clock for the NMOS device, and then you have two different function series and parallel combinations of NMOS pull down stacks that are complementary to each other and that take complementary inputs, and that will produce two outputs that are inverted from each other. And then those outputs can then be sent to a later dual rail domino stage that will do the same thing. And so you can cascade multiple dual rail domino stages in series with each other in order to get your series of logic. Keep in mind, since you're doubling your domino logic, you're also doubling the area that it's going to take up, and likely doubling, not quite doubling your power, because you're sharing some of the footer devices, and so the clock power won't necessarily double, but your power going through your data is going to increase as well. So it will be higher area, higher power, but you will be able to get true and complementary outputs from your logic. As an example of dual rail domino, let's say we want to create a dual rail domino gate that gives us an AND and a NAND function. So AND and then the not AND. So if we're given A and A bar, or in this case we're calling it AH and AL, and B and B bar, BH and BL, we want to compute Y of H is going to be A and B, Y of L is going to be A NAND B. So try to draw out a dual rail domino stage if you want to test out your ability to do that. And you can pause here, and then we'll go through it in a second. So if you haven't paused and you want to, go ahead. Otherwise, I'll go through with the show you the answer. So First thing to note is you want pull-down networks that are conduction complements. So only if one of them is pulling down, the other one can't pull down, and if the other one is pulling down, if the other one is pulling down, then the first one can't pull down. So we typically do that with series and parallel being our complements of each other, as long as we invert the inputs of the series and parallel. So it's similar to what we do with two inputs coming into NMOS and PMOS, because keep in mind PMOS turn on with the complement version of the NMOS, and so having the same input going to NMOS and PMOS, you take the series and change it to parallel, whereas if you're using both NMOS for both of them, you have to actually have the inverted version as you go from series to parallel. So on the left hand side we have AL and BL kind of ORed with each other or NORed with each other. After it goes through the inversion, the overall logical function there is going to be A NAND B, whereas in the case on the right hand side where it's AH and BH, where they're in series with each other, we're going to get, after we go through the inverter following the domino gate, we're going to get an A and B function. So you can see this is a way of getting a NAND and function from, it's kind of one gate, but it's kind of two gates in one, if you want to call it that. We're sharing some logic, mainly the footer device, and we're sharing the clock that goes to the PMOS precharge, but that's about all we're sharing. And then we have separate pull-down stacks, separate inputs, and separate outputs with an inverting stage at the output of the domino stage. One more example that I'm going to show of a dual rail domino, and in this case I'm showing it because it's actually a way that you can share transistors between the two separate sides. So in this example I'm showing an XOR and XNOR function, and you can see that we're sharing the footer at the very bottom between the two stages, and then we're in effect sharing the BL and BH between the two sides as well, because the BH will, you can see the BH on the right hand side of the stack has both the AL and AH in series with it going up to the outputs on either side, and the same thing with the BL is being shared, and it has the AL and AH both each going up to its outputs. And so the footer and the BL and BH NMOS devices are being shared between the two dual rail domino systems. So this is a way, you have to kind of work through the logic. Some places, some types of logic you can share, some types you can't, but you have to be aware of, it's a little bit tricky sometimes to share and make sure that you're not doing something incorrect. So just as an example, this is a good way to try and minimize the additional cost of doing a dual rail domino, where you don't take up quite the double amount of power and area. Over the next few slides, I want to go through some of the drawbacks, some additional drawbacks of domino stages, as well as ways to overcome those drawbacks. So the first of those is leakage. I've mentioned in previous lectures how as we've improved our process technology and decreased dimension sizes over the last 10, 20, 30 years, devices are getting higher and higher leakage, and so we have more power lost through leakage and other effects. One of those effects can dramatically affect domino nodes. Keep in mind that the way the domino node works, when we go into pre-charge, we're charging up our output node of the domino, and we're charging up a capacitance effectively, and we want that charge to stay at VDD. The problem is, with our transistors becoming more and more leaky, even when we try to turn them off, we still have current through the devices, even when we think we're never fully off. We always have some amount of leakage current. And so that value of VDD on our output node will slowly decay as we're leaking and we have charge leakage through the NMOS pull-down stack over time. So years and years ago, you maybe had milliseconds worth of time in order to try and make sure that you didn't lose your value there. Now we're nanoseconds or below nanoseconds, down in the picoseconds range, as to how long you can let the value stay there and still have a good VDD value. So one of the ways we overcome this is similar to the way that we use feedback in a latch or flop in order to hold a state value. We can use a keeper in order to hold the dynamic node at this value. And in this particular case, usually when we have feedback in a latch or flop, we have a inverter feed forward and then an inverter feeding back, and so we have kind of back-to-back inverters. For a domino node, we only need to keep the value of 1. If we have an input, like our input A come in, and A comes in high and pulls the output low, we don't need something to hold it low, because that's what the input A is doing. It's pulling it low and holding it there. So we only need something that will hold a value of 1 if the inputs don't try to pull it low. So we have, as shown here, an inverter that is sampling our output node X and feeding back the output of the inverter to just a PMOS keeper. And that value, if the value of X is a 1, the output value Y will be 0, feeding back to an PMOS device. A 0 going into the gate will have that gate on and try to keep that PMOS device will be pulling the X up to 1 and keeping it at a 1. But we don't want that PMOS device, we want it to be very small for the most part, because it's only there to hold for leakage and not trying to actually pull up the node. And so we want to keep it pretty small and weak, so that way when we try to evaluate, if A comes in and A goes to a 1, we want it to be still pretty quick and to be able to fight that keeper and override the keeper pretty quickly, so that our output value still goes through the gate really quickly. Another problem that we have with domino gates is what's called charge sharing. And in effect, this is where when we pre-charge our domino gate, if we look at the circuit shown in the lower left here, we have a NAND type circuit where we have A and B, two series devices. And when we're in pre-charge and our clock is coming in and it's low, it's pre-charging the value of Y. But it's not necessarily doing anything to the intermediate node between transistors A and B. So the value of X could be a high value, could be a low value. It just depends on what might have happened the previous cycle or previous several cycles. So if we assume, for just sake of argument here, that the value of X has been discharged and is at ground, and the value of A is low, it's not going to be pulling X up. The A transistor is turned off. The B transistor, maybe in a previous cycle, has already discharged the value of X, and during pre-charge we're only charging up Y to a high value. So what happens if, as shown on the right here, our clock goes from low to high, so we go into evaluate, and then our value of A goes from low to high, but the value of B stays at 0. what happens is A turns on and it allows charge to flow between X and Y. And so you can see X will get charged up a little bit because it's trying to equalize to Y, and Y will get pulled down a little bit because it's trying to equalize to X. And so this charge sharing noise will cause the value of Y to decrease from VDD by a certain amount, and we need to know how much that is. So if we look at the value of X will equal the value of Y, and it will be sharing the charge, so it will be effectively a charge balancing between CX and CY. So the total voltage now on both nodes is going to be CY over CX plus CY times VDD. So this can be a problem if this intermediate value of X, so in maybe a 2-input gate like this, maybe it's not quite as big of a problem, but there can definitely be times where you have multiple inputs, multiple nodes that are charge sharing, and you can have actually a significant amount of charge sharing that could bring your value of Y down to maybe even half of VDD, depending on how complex your gate is. So this can be a really big problem because it can make it look like you're trying to switch from high to low when you really shouldn't be. So next foil, I'll go into how we can try and overcome this problem. The way that we can overcome the charge sharing problem is to have a secondary precharge device. So instead of just precharging our output node Y with our clock, as shown in the circuit, we have an additional PMOS device that's shown in blue that is added and precharges the internal node between A and B. And so this is called a secondary precharge transistor, and we don't, the bullet point that's under there about we typically need to precharge every other node. So if we had a more complex structure that maybe had 4 transistors in a row, for example, A, B, C, and D, we wouldn't have to precharge the A to B and B to C and C to D nodes. We would be able to do the A to B and then maybe ignore the B to C and do the C to D nodes. And the reason for that is a little bit complex, but effectively what winds up happening is as your inputs are switching, so as A is switching from low to high, keep in mind there's a gate to drain and a gate to source capacitance as well. And so just the fact that your input is switching from low to high is injecting some charge into your source and drain capacitors that will offset the fact that the internal nodes could be at ground. And so in effect, when your inputs are rising from low to high, they are injecting some charge into the capacitor at the output just by nature of the fact that you have gate capacitance to your source and drain. So that will help offset some of the internal charge sharing effects that you might have. And so it in effect means you only need to adjust for about half of your internal charge sharing. And then the final note here is if you have a large capacitance on your output node, so if you're trying to drive a fairly big load, that will actually help you as well. But you can't count on the fact that you're driving a big load, so if you're designing the domino gate, you should design it with the secondary precharge devices in there in order to make sure that you don't get this charge sharing effect causing a transition when it shouldn't be detecting a transition. Another problem that domino gates have is their noise sensitivity. They're actually very sensitive to noise sources at both their inputs and their outputs. So at the inputs, keep in mind that normally with a static inverting gate, if we have our PMOS and NMOS balanced as far as their drive strength, the input has to get close to about VDD over 2 before we start seeing the output switch. Or, we have the VIH and VIL, and that needs to get, maybe up to, 1/3 to 2/3, or for the input. If the input was switching from 0 to 1, we would maybe need to get up to at least 1/3 of VDD before we would see our output start to switch at all. But for domino gates, since we don't really have something fighting the pull down, we only have, when the NMOS starts turning on, it automatically starts pulling down. We don't have a PMOS fighting it other than the weak keeper. And so as soon as we get above the threshold voltage of the NMOS, it starts pulling down. And so any amount of noise on your inputs is going to cause a lot of noise on the output. Similarly, if we have the output node itself only has a weak keeper on it. And so if we have our output of our domino, if it happens to run a long distance, so if it's a metal wire that goes 50 microns or 100 microns or something, and we have another metal wire running next to it that the two metal wires have cross-coupling capacitance on them, if the other metal wire transitions from a 1 to a 0, it's going to inject noise on the output, and there's not going to be something really fighting it other than, again, the weak keeper. So the noise sources that we have capacitive crosstalk that could happen on both the inputs. So if we have a upgoing noise on your inputs or capacitive crosstalk of downgoing noise on the output, we could wind up accidentally discharging the domino node when we didn't want to. We have the charge sharing from the internal nodes, and then we also have power supply noise. Power supply noise can affect even static circuits, but they're just going to affect domino circuits more because they don't recover as well. There's other noise sources as well, but these are the main noise sources that wind up hitting domino nodes. And as I said, they're very sensitive to it, so they will propagate the noise forward. And if you have multiple domino stages, one after the other, the noise will kind of amplify from stage to stage. So the first stage, you might see just a little bit of noise, but then since the output of the domino stage will have a little bit of noise on the inputs to the next stage, it'll get amplified from stage to stage. So you might see the first stage, you have just a little bit of noise, and by the time you get through maybe 3 stages, you have a total failure. So it's something you definitely need to have tools to check domino noise specifically differently than normal static noise because they're so sensitive to it. And the last issue with domino, kind of the last drawback of domino that I'm going to talk about in this particular set of lecture, is the power issue. And effectively, domino gates have a high activity factor compared to static gates. Keep in mind that the output needs to pre-charge and evaluate every cycle. So every cycle there's a pre-charge and a potential evaluate. And so just envision, for example, if we have a static circuit whose input, like let's say if we have a static NAND gate, whose inputs are both high, and if the inputs don't change for 4 or 5 cycles in a row, the output's not going to change. So we have no transition in a static NAND gate whose outputs don't change. The inputs, I mean whose inputs don't change. So a static NAND gate, both inputs are 1, the outputs is a 0, and if they stay a 1 for 10 cycles in a row, the inputs stay a 1, the output stays a 0 for 10 cycles in a row. there's no power consumption other than just leakage power. In a domino gate, on the other hand, if you have both inputs are 1 and the clock goes into evaluate, the output had been pre-charged to a 1 and it goes from a 1 to 0, and so you're evaluating to 0, and then the next phase of clock you go back into pre-charge and you pre-charge it back to a 1, and then you go into evaluate and you evaluate to a 0, and every cycle you're charging and discharging that node. And if you have multiple domino stages in a row, you might be charging and discharging multiple stages in a row every single clock cycle, whereas static gates would not have that type of transition. And even in the case where your domino gate isn't evaluating, you still need to send a clock to the pre-charge and footer device of your domino. And so that clock is consuming power even if none of the domino stages are evaluating. You still have clock power that you don't have if you just have static stages. So both of these issues lead to very high power consumption for domino stages compared to static, and is one of the reasons why they're not in nearly as much favor anymore as they used to be, because power is much more of a concern than it was 10 to 20 years ago. The final summary of domino is domino logic is attractive for high-speed circuits if you don't care about power and area and several other concerns. So it can be 1.3 to 2x faster than static CMOS, but it does have many challenges, as I just went through: the monotonicity, the leakage, the charge sharing, noise, and power challenges of domino are all things that are difficult but not impossible to overcome. I worked on domino circuits for the first 8 to 10 years that I was at Intel, and it was definitely the thing that we used in areas where we needed speed. And it was used quite extensively in high-performance microprocessors in the 1990s, and even early 2000s when speed was king, and everyone wanted the fastest thing that was out there. And then in the early 2000s, somewhere around 2002 to 2004, maybe 2006, somewhere around 2006, it started becoming less and less used and only used in very selective places where the most critical places in the entire chip, as we were trying to reduce power. And nowadays, for the most part, domino is pretty much just used in memories, register files, ROM, PLA, that type of thing, where it's very special usage, and they try to use it in ways that don't consume massive amounts of power. But yeah, power is the limiter, and as the last bullet point says, it's still used in memories, mostly for the area efficiency that we can get, and very specific usage in memories. So, yeah, if you have something, I know there's still custom uses out in industry, maybe not for more general purpose microprocessors and large usage, but for very custom usage where somebody still needs the very fastest, and they can make do with the power consumption that a domino has, it's still useful. So over the next couple of slides, I'm going to go through a couple other types of circuit structures that are, and types of circuit logic that are used. I'm not going to go into a lot of detail with each of these because I don't personally recommend using most of these types of circuits or types of logic, but I want to mention them just so that you're aware that they exist, and if you run into them in the future, it is something that can be used. You just want to be careful on how you use it. So one of those is using pass transistor circuits to do logic. So if we use our pass transistors like switches in order to do logic with them, in effect instead of having our inputs drive into the gate of a transistor, we have our inputs drive into the diffusion terminals of transistors as well as the gates. And by a combination of using the gates and the diffusion, we can get different logical functions out. You might have seen earlier in the book, I think they presented a version of an XOR function that used pass-gate transmission logic. And I can't remember, I know I showed it on the board in class, using something like a 2-to-1 mux in order to do an AND function instead of a NAND function. So you can use transmission gates to do things like that. One example of using transmission gates is our 2-to-1 multiplexer, where we have two pass gates with an A and B input and a select bar input, and that's used quite commonly, and obviously we use 2-to-1 muxes all the time for various different circuits. And so it's not that pass transistor logic is inherently bad, but if you're taking this to a little bit more farther extension, you would maybe have multiple pass gates in series with each other trying to do a more complex logical function, and that's where it can get a little bit more difficult to make sure you don't run into problems with noise or not reaching full rail and other issues where pass transistor logic can get difficult, and it's also very difficult to tell whether what you're making is going to be functional when you get your actual silicon out. So running the right the tools that we use to verify our logic don't necessarily work well for this type of logic as industry level tools. So one last comment is, if you really want to make sure that you're safe, you should have some sort of gate at the end of your pass transistor logic that restores to a good driving of a 0 or a 1 function. For example, with our 2-to-1 mux, you can just have two pass gates and have the output Y, but it's a lot safer to at least make sure that you have an inverter that drives the value full rail at the end, and you have a good drive strength, so you know whatever you might drive into next has something that at least has a good drive strength to it. Now, as an addition to pass transistor logic, there's a type of logic called LEAP, which is lean integration with pass transistors, where what we're trying to do is simplify our logic, or shouldn't say simplify our logic, remove some of the transistors to make the area in the layout and the amount of capacitance that you have to drive through your select and your A and B inputs to minimize that as much as possible. So in this case, we're getting rid of our PMOS transistors since our NMOS have better drive strength, and we use the NMOS transistors to either drive high or low. Obviously, the NMOS transistors can drive low better than they drive high, but when we're trying to drive high, the problem there, as we said before, is an NMOS can't drive all the way to the rail. And so we solve that in this LEAP concept by having, after we go through the combination of whatever the pass transistor logic is, in this particular case, it's either A or B depending on select. After we go through that, we have in a static stage to give a nice output drive strength, and we'll use the output of that inverter to feed back and have basically a weak PMOS feedback device. And what that does is, if the input, like let's say input A is high, it will pull up to within a VT of VDD, and then the weak PMOS pull-up device there will be able to pull it up the rest of the way to high. The thing to keep in mind here is we need to make sure that PMOS device is weak enough that it doesn't slow down too much if we're trying to drive a low value in. So if A changes from a 1 to a 0 and tries to pull the output of the pass transistor logic low, we want to make sure that it can do it pretty quickly, and that it actually has the drive strength to override the PMOS keeper that's there. So there is a ratio constraint of the NMOS to the PMOS, and it will cause some amount of slowdown, and you want to make sure the PMOS isn't enough to override the NMOS and keep the value high. One additional variation of the pass transistor logic is called CPL, which is complementary pass transistor logic. This is similar in a way, if you want to think about it, of like the dual rail domino, where we're creating a dual rail form of pass transistor logic. So we have the same pass transistor logic we create a complementary version of it, where we have, instead of just A and B coming into the logic, we have the complementary version where A bar and B bar are coming in, and we create the output of each of those are going to be an inverted version of each other. And so then we'll get our output will be both Y and Y bar. And by doing this, since we're getting a Y and a Y bar out, we will be able to feed those values into some sensing logic or whatever, and we as long as we know that there's a delta between Y and Y bar, we can figure out which one is supposed to be high and which one's low. It avoids the need for the ratioed feedback, because we can put in this cross-coupling feedback between the two sides, where one side is driving the PMOS of the other side, and that way as one gets fully switched, the other one will turn off. So one of those PMOS will turn on and one will turn off based on the fact that the output node of one side is going high and the other side is going low. And those cross-coupled PMOS devices will provide the ability to pull the output node that's supposed to be high up to its full rail value. And so because of the fact that we're using this cross-coupling for the feedback, we don't need to worry as much about the size of the PMOS relative to the NMOS, other than initially, as it's in the first process of switching, you might get a little bit of contention, and so you still don't want those PMOS to be too big, but you don't need to worry quite as much about the PMOS being able to override the NMOS, because eventually it will turn off as the other side goes low. As the other side goes high. So as one side goes high, it'll turn off the PMOS on the other side. And the final summary about pass transistor logic, as I kind of mentioned when we started this section, is it's not really in use much anymore. Researchers investigated using pass transistor logic for kind of general purpose applications in the 1990s, but the benefits over static CMOS were small or even negative, and it's no longer generally used. There are places where pass transistors still have a niche in specialized circuits. When you look in memories, again, memories have a lot of specialized things where they use pass transistors, but generally even in memories it's just a single pass transistor that's being used, and then it's being sensed after that, and so it's a very specialized niche for even memories. There was actually one place where we used pass transistor logic. I was on a project where we used it inside a microprocessor, and we were trying to use it to actually save power. We were using it in low voltage swing application where we weren't trying to get to full rail. And it turns out even for that usage, when we had to account for all of the negatives that pass transistor logic produced, we probably wound up using about the same amount of power or even more power, even though we were trying to be the low voltage swing was mostly trying to be for power reasons. In effect, didn't even give us that. So it was something that worked. We had it working on the chip, but it was a lot of effort, a lot more effort than just using static CMOS would have been. And we only used it for one project, and then we converted it to Domino after that. So it's not something that is easy to use, and probably not something that you really want to do unless you really know what you're doing.